Steel serves as the backbone of many construction and fabricating industries, providing strength, stability, and durability. One of the most important criteria in the selection process of a steel material is hardenability. Knowledge about the hardenability of steel is necessary to be able to select the appropriate combination of alloy steel and heat treatment to manufacture components of different sizes to reduce thermal stress and distortion. What is the hardenability of steel? The hardenability of steel is the ability of steel to partially or completely transform from austenite to martensite when cooled in a given quenching medium. This involves a rapid transition from a state of 100% austenite to a high percentage of martensite. Hardenability is the property that measures the depth and distribution of hardness by the formation of martensite in the steel upon quenching from high temperature. Note: hardenability should not be mistaken for hardness. It is important to distinguish the difference between hardness and hardenability. Hardness is the measure of a material's resistance to indentation or deformation. It is applicable for materials or metals, while hardenability is the ability of a steel to form martensite by quenching. It applies to steel only. Test for hardenability. The Jominy end quench test is used to test the hardenability of steel. In the end quench test, a steel sample that has been normalized and machined to eliminate decarburized surface is heated to the austenitic temperature, about 800 to 900 degrees Celsius, for some minutes for it to be austenized. It is then quickly transferred to the test apparatus that holds the steel sample in a vertical position, and a jet of water is sprayed under controlled conditions at the bottom end of the sample. The end of the bar is thus cooled very quickly, while the cross-section from the other end is cooled more slowly. The cooling rate varies along the length of the sample. After cooling is completed, the hardness is measured at intervals from the quenched end. The relationship between hardness to distance from the quenched end is an indication of its hardenability. Factors that affect hardenability. The major factors that affect hardenability in steel include: 1. Carbon content of the steel. 2. Austenite grain size. 3. Alloying elements. The carbon content of the steel. Carbon controls the hardness of the martensite. A greater percentage of carbon present in steel will increase its hardenability. It increases the hardenability by hindering the formation of pearlite and ferrite. Increasing the carbon content makes the steel harder and stronger but less ductile. Austenite grain size. An increase in austenitic grain size increases hardenability. It is at the grain boundaries that the nucleation of pearlite and bainite occurs. An increase in the austenitic grain size will lead to fewer grain boundaries. Therefore, the available nucleation sites are decreased, which reduces the rate of formation of pearlite and bainite, and more opportunities for martensite to form. Alloying element. The main alloying elements that affect hardenability include boron, chromium, manganese, molybdenum, silicon, nickel, vanadium, and cobalt. The addition of alloying elements increases hardenability except for cobalt. Cobalt decreases the hardenability of steel by accelerating and strengthening the formation of ferrite. The other alloying element increases hardenability by preventing phase transformation from austenite to ferrite and pearlite. This is a result of the redistribution of the alloying elements during the diffusion phase transformation from austenite to pearlite and ferrite. Other factors that can affect hardenability include the geometry of the specimen and the quenching medium used. The geometry of the steel, that is the size and shape, affects the martensite transformation process. The rate at which the interior of the specimen cools is dependent on its surface area to volume ratio. The larger the ratio, the increase in martensite formation. The type of quenching medium also affects hardenability. Using water, oil, or air will produce different hardness in the interior of the workpiece, although water is usually the medium of choice.